All right, you guys, it looks like it's ready for us to start. So, couple of quick reminders. Exam 3 is just around the corner. It's going to be on April 9th. 6:45 is the official start time, but if you show up at 6:30, we can get everybody started at 6:35. The study materials are posted on Canvas, and review sessions will start next Friday, and then there'll be one on the immediately following Sunday. All right. A couple things I wanted to just remind everybody. Hopefully this is second nature to you at this point in time. Very generally, first law, change in energy of a system is due to energy transfer due to heat and work. And because this is a state function, we can choose a reversible path to get between our initial and final states. If we impose a limitation on this and talk specifically about ideal gases and limit our discussion to pressure volume work only, then what we can say is that the change in the energy of the system depends on the temperature through the heat capacity. And that's because we've shown that the energy of an ideal gas depends only on temperature and the number of particles. Right? Also, with the limitation of pressure volume work only, du is going to be the heat transfer minus PdV, or, because it's an ideal gas, minus nRT over VdV. So in today's lecture, I'll be referring back to these equations as we do some derivations. All right, things that we talked about last time. We basically introduced an identity called the Stirling approximation. It's an identity as long as n is very large. We won't use that probably until Friday or Monday. We also talked about changes in energy as a determinant with regards to spontaneity, whether a process will occur or not. And basically what we've shown is that we need to think about something beyond the energy changes of the system, because we looked at a number of processes that either require the input of energy or we have delta U is equal to 0, and yet they occur spontaneously. That led us to say that if we're not at equilibrium and we have a system that's isolated, that system, when it moves towards equilibrium, we see an increase in the disorder or the randomness of the system. This is something that we've done previously in homework, but we've basically shown that dq over t is an exact function, therefore an exact differential. ds is an exact differential because of the definition of entropy, and what we can conclude from that is entropy is a state function. And we'll be showing through some examples looking at expansions of an ideal gas via multiple paths, just like we've done in chapter 5, that entropy is a state function. So we'll demonstrate it. Now, we didn't show this yet. We were pretty close to doing this. But at any rate, what we will see is that if we're talking about an isothermal expansion or compression of a gas that's performed reversibly, the change in the entropy of the system is given by number of moles times the gas constant natural log V2 over V1. We will explicitly derive that from multiple directions, right? Very important, and I've alluded to this before. In thinking about entropy changes, it's really important to think about the system versus the surroundings versus the universe. So it's really important to delineate those, right? So we're going to be doing some calculations, looking at delta S for expansion compression of ideal gases. From there, we're going to talk qualitatively about the change in entropy that's associated with a change in heat. And actually, I think we'll do a little foreshadowing on that. So, from the definition, ds equals dq reversible over t. So if I'm talking about my system, and if I add heat to the system, what's the sign of dq? It's positive, right? And temperature is always positive, right? And so that says if I add heat to a system, its entropy has done what? Or will do what? It increases. And it also says that if I remove heat from a system, I'm going to see a decrease in the entropy. And so if I have a block of iron at 100 degrees and a block of iron at 10 degrees, the entropy of the iron at 100 degrees is greater than that at 10, right? So qualitative. All right, we're not gonna get there today, so we're not gonna bother talking about that yet. Okay. All right. So where we left last time was we were starting to talk about delta S for the isothermal path, and basically we're up to this point where we said we want delta S for path A. We know that that's going to be the integral between our initial and final states of dq over t. So I come back up here and I see that dq for the reversible path is nRT over v dv. All right? So I'm going to say we're going to integrate nRT over v dv. Right? At this point, all that I've put in here is dq reversible. So to get this to be delta S, I need to divide that by t. All right, and we're going to be going from V1 to V2. Pretty clear. Temperature's going to cancel. All right. Number of moles is constant. R is a constant. That comes out front. So I can say NR. Right. That leaves me with the integral of dV over V. And what is that? ln. Thank you. Natural log V2 over V1. Right. So that's delta S for path A from the system perspective. Does that make sense? Okay? All right, this is pretty important to recognize. All right, so that's going from this initial point to that second point, right? Now we know that entropy is a state function. We've demonstrated that ds is an exact differential. So if I go through path B plus C, delta S for that path should be the same as that, right? All right, so we're going to demonstrate that. All right, so path B is our adiabatic path, right? So here we're going to be saying we're going from our starting point to our ending point, dq reversible for path B over t, right? And because this is adiabatic, what can we say dq is? That's going to be 0, right? And because that's 0, the whole thing is 0, right? Okay, and that should make sense in terms of our definition of entropy, right? ds is dq over t. If dq is 0, if I'm not adding heat or taking heat out of the system, there's no entropy change. Okay? All right, so for path B, or C, sorry, we're going from here to here, all right? So for path C, we have constant volume. What's the name that we've given to that process? Isochoric, all right? So this represents isochoric heating. All right? And along path C, if I'm holding volume constant, that means that PdV is equal to 0, all right? So we can say that du is equal to dq reversible. All right, so path C, du equals dq reversible. And because we know we're changing the temperature, du is going to be Cv dt. All right? And if I want to integrate this, I will say q is equal to the integral Cv t dt between t1 and t, or t2 and t1, sorry. All right? Make sense? All right, so we want to look at delta S for this path. Well, delta S for path C will be integral from state 1 to state 2 dq reversible over t dt, all right? Or not dt, just dq reversible. All right, and what we've just stated is that this dq reversible Cv dt, right? And so that means we're going to be integrating Cv t dt over t dq over t between t2 and t1, right? So if I step back a second and say, well, path B has 0 delta S. Path C has this integral delta S. And what we know is it has to be the same as this, all right? And so what we're going to do now is we need to show that this and this are the same, okay? All right. Give me a second. I just want to make sure. So what we're going to do is look at path B. So before we go forward, let's talk again about path B. So path B is our adiabatic path, right? So that means that CV dt is the same as du, right? And if it's adiabatic, the only thing that I've got going on is work, right? Because dq is equal to 0. All right. So we can say that du is equal to dw reversible for path B, which in turn is equal to CV t dt. Okay? All right. And then, of course, we know that this work is the same as minus nRT over V. We agree? dV is equal to CV t dt. Okay? Make sense? Everybody follows that? All right. So then I'm going to take this equation and I'm going to divide both sides by t. All right? And you might say, why am I doing that? Well, keep in mind that I'm trying to get at this expression, right? So if I take both sides, divide by t, I get there, right? So that's going to get me minus nr over v dv is equal to cv t dt. Okay? All right, and then we have to integrate it. And I'm going to scroll back to our picture for a second, because again, what we're talking about is looking at path B. Right? And so our integral will be our initial temperature is T1, our final temperature is T2. This is going to be integral. Oops, and I forgot to divide both sides by T. T1 to T2. Make sense? All right, now I look at this and I compare it with that, and I see those are the negative of each other, right? Okay? And so what I can say then is that delta SC is equal to minus the integral T1, T2, CV t over t dt, which in turn is equal to plus nr over v dv. And I forgot to integrate this side. Okay? Integrate both sides, v1 to v2. Okay? All right. And so what you can do is then the integral. Let me fill this out, v1, v2. All right. This integral is going to be nr ln v2 over v1 as we expected it to be. Okay? All right. So now I have delta S for path B and delta S for path C, and that pretty straightforwardly goes to B was 0 plus nr ln v2 over v1, and as we expect, we have the same delta S as for the isothermal process. Delta S for path A. Okay? All right, so we've demonstrated that delta S is a state function, right? Okay, we're going to do one more round of that. And, you know, this parallels what we did with Chapter 5, paths D and E. So for paths D and E, before we go through it, let's remind ourselves of what's going on. All right, so for path D, what are we holding constant? Path D, we're holding pressure constant. And we see that we're going from a lower volume to a higher volume. So that basically means we're doing constant pressure heating. All right? And then whenever I get to this point where I've got P1, V2, T3, then I'm doing an isochoric cooling step. All right? So we need to talk about the heat transfer for each of those steps and then use that to determine what delta S is. Okay? All right, so for path D, we know that that's going to be given by dq reversible plus dw reversible, right? And because what I'm interested in is getting the heat transfer for that path, I rearrange this and say that my reversible heat transfer for path D is going to be du, the change in the energy of the system, minus the work, dw, right? And we know that du is, for an ideal gas, Cv dt, and work is going to be minus pdv, and because I'm subtracting it, that makes it go plus pdv, right? Now, to indicate that this is a constant pressure process, we're at P1, I'm going to put a P1 down there. All right? All make sense? Okay? All right. So if I want to determine then what the total heat transfer is, then what I need to do is integrate, right? And so that means I'm going to integrate from T1 to T3, Cv T dt, right? And the integral of this term, I know the pressure is constant, so this just becomes P delta V, right? P1 delta V. Okay? Make sense to everybody? All right? Okay, so we look at path E, which we've said is the isochoric cooling step, right? So in this case, the only thing that's occurring is heat transfer, right? We're removing heat from the system, right? So this is going to be dq reversible for path E, right? And because we know we're changing the temperature, du is also equal to Cv dt. So we can say that dq reversible for path E is the same as Cv T dt. Okay, so I have now an expression for our heat transfer, right? And if I want to know the total heat transfer, then I need to integrate. So we're going to integrate here, and we're going from T3 back to T1, Cv dt. Okay? If I wanted to know what the total heat transfer is for path D plus E, I'm going to take this term and sum it with that term, all right? And I was planning to write it all out, but it will take a little bit too much time. So if I take this, add it to this, what happens to these two terms? They cancel. We go to 0, right? And I'm left with P1 delta V, all right? All right, so if we go back and look at all the heat transfers for these 3 different paths that we've taken, we find that they're all different, right? Just reiterating that heat is a path function, all right? But if we look at delta S, we have a different story, all right? So delta S for path D is going to be, for completeness, let me write this out, initial to final, dq reversible path D over T, right? This is dq reversible, Cv dt, P1 dV. So I'm going to divide through by T, Cv T dt over T. I'm going to be integrating from T1 to T3, right? So that takes care of this first term, right? Now we also know that the pressure can be written as nRT over V, right? And so I'm going to do that, nRT over v, and then I divide it by t, and I multiply that by dv. We're going to integrate from v1 to v2. Again, our t's will cancel. All right? And this is going to be the integral t1 to t3. cv t dt over t plus, all right, and then we've done this integral 2 times today already. That's going to be nr ln v2 over v1. Okay? Oops. Any questions about anything that we've done so far? Everybody following? Make sense? All right. We don't look enthused today. All right. But I know it's the middle of the week after spring break, and everybody's probably thinking about Friday already. Is anybody thinking about Friday already? Yeah. Okay. I'm thinking about a nap, actually. All right. And then we can do the same thing for path E. All right. So I decided, because this one's pretty straightforward, just to do this in one step. So dq for path E was cv dt. To get from there to ds, I'm going to divide by t. So I have cv over t, and then I need to integrate it between t3 and t1. Okay? All right, and then I want to know what the overall delta S is. Right? Well, that basically means I'm going to look at this term plus this term, right? And what we see is that we've got this integral, t1 to t3, which is identical to this integral, but the limits are reversed. So again, that goes to 0, and I'm left behind with nr ln v2 over v1, which we have seen is the same as delta S for path A, which is the same as delta S for path B plus C. Okay? We good? All right. Okay, so we've demonstrated from 3 different perspectives that entropy is a state function, and clearly heat is not. Okay? All right, so what I want to do is I want to take a moment. I've added an extra page in here, all right? Because right now, all we've talked about up to this point is delta S of the system. So I want to look at a little broader perspective, look at delta S of the surroundings, as well as delta S of the universe. So specifically for reversible, isothermal, expansion, or compression of an ideal gas. And what we've demonstrated is that delta S of the system for this process is given by nr ln v2 over v1. Okay? All right, so all I've done is just reiterate what we've done up to this point. And what I want to remind everybody is that this is basically the same as integrating from our initial point to our final point, dq reversible, for our system over the temperature, right? Because this is the same as this. Okay? All right. So then we want to talk about delta S of the surroundings. So delta S of the surroundings will be the integral from our initial state to our final state, dq reversible over t. But in this case, because we're talking about the surroundings, this will be the heat transfer to the surroundings, or with respect to the surroundings. Okay? All right. So now the question is how is this related to the heat transfer of the system? It is equal but opposite in direction, right? Because if I transfer heat out of the system, it goes into the surroundings. And it's exactly the same amount. Okay? All right. So that means this is equal to integral between 1 and 2 dq reversible of the system with a minus sign in front, right? And we already know that this integral is nR ln V2 over V1. So this is going to be equal to negative nR ln V2 over V1. Okay? Does that make sense? All right, and then if I said, well, what's delta S of the universe? That's going to be the sum of the entropy change of the system plus the surroundings. Delta S universe equals delta S system plus delta S surroundings. And in this case, what does that come out to be equal to? That's going to be equal to 0, right? Now, this was derived explicitly for a reversible isothermal process. And the key part of it is reversible. If you remember, when we've defined a reversible process, we've said that a reversible process is a process in which we are at equilibrium every step of the way. Right? And if you think about it, if you're at equilibrium, there's no impetus to go forward or back. Right? Right? So what we can conclude from this is if we're at equilibrium, delta S is going to be equal to 0. All right? So delta S of your universe or your delta S of your isolated system. Okay? Does that make sense? All right. We've also said that reversible processes are limits, and we don't often see them in the real world. Right? And so what we're going to see in general, if we have an irreversible process, delta S won't be equal to 0. It's going to be greater than 0. Right? But we're going to demonstrate that. All right, so let's talk about some qualitative things. So we've already discussed the sign association. So if I add heat to a system, that means dQ is positive. dQ reversible greater than 0. And that results in an increase in the entropy. All right. That also means the opposite. If I remove heat from the system, dQ is negative, and ds will be negative. Okay? All right, the other thing I want to do is I want to take a look at what happens if I add the same amount of heat to systems at two different temperatures. Right? And this is just a demonstration, and it's not good mathematics. Right? So I'm just letting you know this is an approximation. Right? Because we know that dQ is infinitesimal. Right? So my first violation of that is I'm going to say let dQ be equal to 1 joule. Right? And then I want to see what impact that has on ds of a substance at two different temperatures. So I'm going to create a little table. I'm going to have 10K, and I'm going to have 10 to the third K. So it's 1,000. All right? And then we're going to say ds. I'm going to put that in parentheses because this means it's an approximation and I'm playing bad arithmetic. All right? So this will be given by 1 joule over 10K, which gives us 0.1 joules per K. Okay? All right, so this says that if I add a joule to my system at 10K, I see a change in entropy of 0.1 joules per Kelvin. If I do the same amount of heat transfer, 1 joule to a hot object, 10 to the third K, I end up with 0.001 joules per Kelvin. All right? This basically says that, if we step back and look at it big time, a bigger picture, adding the same amount of heat to two objects, the one that's hotter is going to have a smaller change in entropy. All right? Does that make sense? Right, so what does that mean? Right. So ds is greater for the lower temperature system. Right. So the way that you can look at this is that we have associated entropy with order. Right. So this represents highly ordered system, lower temperature. Higher temperature, more disordered system. Right. If I increase the disorder by the same amount, the absolute same amount, we see that going from order, this is much more disordered than starting with a higher temperature system, which is already disordered, and we add a little bit more disorder to it. Right? Does that make sense? Okay. The way that your textbook words it, and this is succinct, if we're at lower temperature, we have more order or lower disorder. And that means that if I add heat to that system, there's more order to be disordered. Okay? All right, one of my colleagues, anybody know Professor Venditti? Nobody? Vincenzo? All right, so this is his kid's room, right? So this represents low temperature state, highly ordered. High temperature state, not so well ordered. If we increase the disorder, in this case, it goes much more disordered, right? If I'm at a higher temperature, I've got a lot of disorder, and then I only see an incremental increase in the disorder. Okay? Right. Let's see. At this point, I think what I want to do is we're going to work on a quiz together. Find a team if you'd like. All right. And if you pass this down there, are you a team? You want to be a team? If you could pass one down to the other end, that would be appreciated. Okay, we've got you. Thanks. This is where I start to get worried. Can you guys divide yourselves into two teams back here? Does that work? Right. I mean, I can print some more out, but that's what I got. All right, what we're going to do is part of this we're going to work together, and then there'll be a couple questions that I'm going to let you guys work on your own. All right, so let's talk a little bit about the problem. We've got two pieces of aluminum, all right? And we're putting those two pieces of aluminum, we're isolating them from the rest of the universe. One of them's hot, one of them's cold, okay? Right? And they can't exchange with the rest of the universe. So everything that occurs has to occur between those two blocks, all right? What do you expect to happen? Yeah. The temperatures will equalize, right? So the hotter one's going to get cooler, the cooler one's going to get hotter, right? Which way does heat flow? From hot to cold, right? And the Q from the hot is related how to the Q from the cold? They're going to be equal to each other, but opposite direction, right? Because if the hot one loses 10 joules, it goes into the cold one, and it's going to get exactly 10 joules, opposite sign, right? So we can say at the outset, QH equals Q cold with a negative sign in front of it. Okay? So this is a goal of trying to get the same, to find out the temperature at the end of this. Right? And what we need to know then is the relationship between the heat added and the temperature change. Okay? All right, the information that we've been provided is the molar heat capacity, a constant volume, right? And the amount of the substance, right? So what we can say then is that Q in general is going to be equal to number of moles times the heat capacity times the change in the temperature, right? Does that all make sense? Right? Because this is Q absolute value, not dQ, I need to integrate this between T1 and T2. Does that make sense? All right, so let's set that up. So for the hot side, that means I've got integral. Our initial temperature for the hot one is 900 Kelvin. We don't know the final temperature, so I'm going to put TF in there, right? Number of moles for the hot, heat capacity of the hot, dt, is equal to a negative of the integral from 300 K to the final temperature number of moles of cold, heat capacity of the cold one, dt. All right? So let's step back and look at this a little bit. All right? So I've chosen to make both of these blocks have the same number of moles. Right? And so that means NC is the same as N, the other N. I don't know how to change the color of my pen here. Oh, there we go. All right. So what happens to N on both sides? It cancels. Right? I've also chosen the same material. So aluminum and aluminum. So what happens to the heat capacities? They're going to cancel. Right? So all right. So that really means that I have left the integral of dt, which is going to be delta t. Right? So for the left side, that's going to become Tf minus 900K. And for the right side, that's going to be the negative of Tf minus 300K. All right? I'm going to do a little bit of arithmetic here. So this will be minus Tf plus 300K. All right? And then the algebra says I'm going to add t to both sides. And what do I end up with on one side if I add t to both sides? 2Tf. And what's that going to be equal to? Somebody? 1200. Thank you. And therefore, our final temperature is 600 Kelvin. Right? We step back and say, does that make sense? Well, I have equal moles, equal mass, and I have the same heat capacity. And so that means I really expect that my final temperature is going to be average of the two initial temperatures. Right? This is specific for this example. Right? If I had gone aluminum and gold, wouldn't have been the case, but still going to be calculable. Okay? All right, so at this point we know the final temperature. Right? Then we can ask the question, what is delta S for the hotter piece of aluminum? So that's going to be delta S hot. Right? That's going to be the integral between the initial and the final state of dq reversible over t. All right? Now we come back up here. Q was given by the integral, so dq is going to be ncv dt. ncv dt. We know the limits of integration. Our initial temperature was 900 Kelvin. My final temperature was what, 600 Kelvin? All right. And I left one thing out. What did I forget to do? I need to divide by t. Okay? All right, from here it's plug and chug, right? So N's 2 moles, 24.3 is the heat capacity. So I have 2.00 moles. My molar heat capacity, 24.3 joules per mole per K, right? And then I'm left with the integral of dt over t. That's going to be ln T2, T2 over the initial, all right? All right, so let's take a look at this. This is positive, this is positive. What's the natural log of 600 over 900? Is that going to be positive or negative? Is this 600 over 900, that number's less than 1, right? So it means that the natural log of it's going to be negative. And that's what we expect as our answer, a negative value, because we're taking heat away from that object. And that comes out to be minus 19.7 joules per Kelvin. Okay, why aren't you moving? There we go. All right, we can do the same thing for the cold piece of aluminum. So now I have delta S cold, right? We know that that's going to be the integral from state 1 to state 2 dq over t. All right, so I don't need to write that again. And it's going to be the same general form, ncv over t dt, but our limits of integration are going to be different now, right? So this is going to be 2 moles times 24.3 joules per mole per K, natural log. Now my final temperature will be 600 Kelvin, and our initial temperature was 300 K, right? So this is a natural log of 2. Is that a positive or negative number? That's going to be positive, right? And that means this whole thing is positive, as we expect, right? And that comes out to be equal to plus 33 point, somewhere I got it, 7 joules per K, right? Okay, so let's also step back and talk about this a little bit. We see that the delta S's are different than each other in magnitude, right? And that's because we've just said that if we have a higher temperature object, the same heat transfer will result in a smaller change in entropy, right? So for our colder object, we see a larger change in entropy, all right? And then we put that together and say, well, what's delta S for the whole process? That's going to be delta S for the cold plus delta S for the hot. And that's going to sum to 33.7 joules per Kelvin minus 19.7 joules per K. And that comes out to be equal to plus 14.0 joules per Kelvin. All right? Right. So the overall process, we see the entropy of the system has gone up. Okay? Now we've also established that the heat transfer between the hot and the cold, they're equal and opposite. And there's no work going on. There's no interactions with the outside. So what's delta U for this process? Anybody? It's going to be 0. All right? And that's because we can say that delta U is equal to the total heat transfer plus W. W is equal to 0, right? And all the heat transfer, we've got Q going from the hot, and that's going to be equal and opposite to Q for the cold, right? Right? That make sense? Okay. So, big picture thing, our isolated system, no change in the energy because it's isolated, but we see, because we're not at equilibrium, an increase in the entropy. Right? All right, so what I would like you guys to do, we'll give you 3 minutes. I'd like you to calculate delta U for the hotter piece of metal. All right? So just delta U for the hotter piece of metal. Do that first. And then think about what we've done. We've needed to make some assumptions. And I'm going to help you with that. Look at the heat capacity. Right? There's 2 things that we've assumed in using the heat capacity that we've used. And I'm going to give you 3 minutes, and then we'll collect them.
missed ACS last year though.
Yeah, yeah.
But
I lied.
for the nationals.
Yeah.
I think we were right at the beginning.
Are you guys done?
Yeah, but it's actually do it.
Thanks. Sorry, I didn't mean to poke you in the eye. Are you guys done?
Yeah, we
Oh, okay. All right, time is up.
dropped this.
Oh, I did. Thanks. Thanks. Do we have everybody's? Thanks. All right, so the fully worked out quiz will be posted, once I get the annotated lecture notes up. So in this case where we were talking about the assumptions that we needed to make, well, we talked about work being equal to 0. That meant that we had to have no change in volume, right? That's the one assumption that was necessary, that there was no change in volume. The other was we used a heat capacity that's associated with constant volume, and so that means that really needed to be no change in volume for the heat capacity. The other side of it is that normally heat capacities depend on what? Temperature. We use a temperature independent one, okay? All right. You know what I'm going to do? This is where I ended this morning, so we're going to end now. You guys say thank you. Right? All right, enjoy the afternoon. It's not horrible out. You can't say that every day. I do have graded homeworks 8 and 9. So if you want to get your graded homework back, meet me out in the hall in 2 minutes. Oh.